Okay, in this example, we're going to be looking at the torque created by the gravitational force and buoyant force on a non-constant density sinking object. We have a beam with a density that varies linearly. It has a given density function, a volumetric density function of 1550 kilograms per cubic meter. And that, well, that's at one end, that's at the left end, and it's twice that at the right end. We're told the diameter and the length of the object as well. All right, so this beam is fully submerged in the water and released. What is the angular acceleration of the beam the moment it was released? It is released in this position, so I'll specify that. So this is the release orientation. So the first thing I want to do is show you the key information that we need to solve this problem that we're going to draw on from previous problems. Okay, so there we have it. So from previous lectures, 19 and 20, we know that the center of mass of an object that varies, that gets twice as dense at one end, is going to be 5/9 L. And that's going to be relative to the lower density end. So essentially what I'm saying is that this distance right here is 5/9 L. Okay. Oh, and let's use uppercase L there. All right. And importantly, we know that the center, or rather the moment of inertia about the center of mass, as shown in the figure, and not exactly shown exactly in its position, it's not quite 5/9, but it's not the scale, is 13/162, or whatever decimal that is, ml squared. Okay, so we solved for these. They both required integration. Okay, so we're gonna use that information, and we also want to stop now and find the total mass of the object. So I'll say also so we need the mass of the beam. And really the best way to think about total mass of this object is to think about linear density, which we're not given. So we can think of linear density. We'll use mu. All right, let me write that. So linear, I just don't want to use lambda because we're going to see that for waves. So linear density is going to be mu, okay? And what that's going to look like, and I have, okay, so in terms, I can write the basically what that is it's going to be rho times cross-sectional area. All right, so it's going to be times area, okay, which is rho times pi d over 2 squared. Okay, so that's going to give us the units that we need, which is units of kilograms per meter. Okay, kilograms per meter. Because by including the cross-sectional area here, meter squared, we're canceling out some of the meters and getting kilograms per meter. Okay. So then we want to think about what is the mass. Well, then the total mass is going to be integrating from 0 to L mu dx. Okay. And I'm just calling x this direction. All right. We have x equals 0. All right. And obviously L at the other far end. And so then the function, and this was all in the previous examples that I referenced up here. We did quite similar calculations. And we did a similar calculation for total mass. I just want to call attention to it because it's slightly different here because we do care about the volumetric mass rather than just the linear, or rather the volumetric density rather than just the linear density. Okay, and so then we can put our function in here. Now, what we care about is that it's getting twice as dense, right? So it's a non-constant density. So what I'll do is I'm going to pull out the pi, all the constants in front. So pi d over 2 squared, and the actual function here would be, there's our L, our upper limit, rho naught, okay, which is 1550, and then times 1 plus L, y over L, okay, and then, x over L, no, I switched to y, okay, and then dx. Because the idea there is that when x equals 0, rho naught is, or rho is just rho. When x equals L, right, when we have x equals L, then we have 1 plus 1 equals 2, so we get 2 rho naught, which is twice as dense at the far end. So that's, and this is the same functional dependence we saw before. Okay? So when we solve this integral, we end up with this right here, with our 3/2 rho naught L actually coming out of the integral itself, and we still have the leading constant. Okay? All right, so now we can plug in our values and get our total mass. Okay? Which we care about in terms of strength of the gravitational force. They'll be potentially relevant for the problem, depending on how we set it up, but I want to be general. So let's do this. All right, so pi multiplied by 12 divided by 2, so 0.12 divided by 2. All right, and that's going to be squared. All right, multiplied by 3/2. Okay, then by our far left-hand density, our lowest density, 1550. Okay, and then times the total length of 2.61. Okay. All right, so we get 68.3 as our mass, or 68.6 is our mass. Okay. All right, so now let's think about our forces, right, which are obviously crucial to this problem, and also something new here. So the gravitational force is absolutely going to act here. Okay, so this is our gravitational force because it acts at the center of mass. Okay, and when we know the center of mass from previous calculations. However, the buoyant force acts at the center of mass of the displaced fluid. All right, so I'm going to write that. Okay, so I'll say note. The buoyant force okay, and since the fluid has constant density, then we know that it's going to have to be at the geometric center of the object. All right, so the buoyant force is actually acting right here. Okay, and so we want to find the angular acceleration, so we need to calculate the torques. All right, so I'm going to do that, and you'll see how this works out. Okay, so I'm going to move on here and actually calculate the torques. So we have torque about the pivot, but what's our pivot? Okay, well, we're going to choose the center of mass to be our pivot. All right, because we're interested in angular acceleration, so as long as we use a torque about a chosen pivot and a moment of inertia about that same chosen pivot, then we'll get an angular acceleration as correct. So we just have to be consistent. Okay, and so all of the torques acting on that point. All right, oh, and I'll write the sum here. So I'm really interested in the sum of torques about the pivot. Well, what it's going to be, let's think. Well, we've got the gravitational force and the buoyant force, right? We've got these two forces. Well, the buoyant force acts at the pivot, so it doesn't create torque. So the only torque is that of the gravitational force. Okay? So what we have then is we're just going to have mg times something that I'll call d, and then that's going to equal I center of mass times alpha. Okay? So actually we're getting pretty close here, although we do need this d value. Okay? So let me show that in the figure. So this is d here, which is the distance from the center of mass to the geometric center. Okay, so well, we know, we can make that calculation fairly easy because the geometric center is 1/2. So then d is just going to be the 5/9 minus 1/2. So we'll say, and d is just going to be 5/9 minus 1/2. So here, let's put that in. All right, so there it is in decimal form, which is not the prettiest thing to look at. We could think what that would be in fraction form. Let's change our mode here. Okay, 1/18. All right. So now, to fit our final solution, we can solve for the angular acceleration, and we should get our total mass, so m multiplied by g multiplied by d, all divided by I, center of mass. Okay. And you can kind of see, maybe how some of these variables would be the same, but we'll just plug things in numerically. All right, so let's find up here what the center of mass is numerically. All right, so it would be 13 divided by 162 multiplied by the value that we got up here for total mass, and then multiplied by our length, 2.61 squared. All right. Okay. Oh, got to change our mode back. This is when we do want in a decimal. Okay. So 37.2 kilogram meter squared. Okay. So now let's start combining all our values. So I'm going to take that total mass up here, multiply that by g, which we're taking as 9.8, multiply that by 1/18. All right. And then we're going to divide that by our center of mass right here, and we get 1.00 as our angular acceleration. What a clean number. And that'd be radians per second squared. And obviously that only applies to the moment it's released, because as things change, or basically as the beam starts to tilt, the torque created by the gravitational force, even if the same chosen pivot, will no longer be mgd, it will be mg sine of the angle, right? So we have it will be changing over time, changing as a function of the angle. But the instantaneous initial angular acceleration is 1. All right, thank you.